Hi, my name is Luke Wilson, and I'm joined by John Lockman. We're the chief architects of the Omnia Project, a new open source effort started by Dell Technologies in partnership with Intel to develop a new generation of cluster provisioning and deployment tools for more modern clusters for high performance simulation and modeling, artificial intelligence, and data analytics workloads. So why do we need something new? Unfortunately, existing tools don't really solve the problem for building clusters for modern workload concerns and for modern system designs. We think next generation research compute platforms are going to be very different from what we do today. Instead of building very homogeneous systems where every compute node looks exactly the same, we're going to be building heterogeneous architectures full of dense compute nodes, full of various different types of accelerators with GPU and FPGA, as well as special purpose ASICs intended for things like deep learning training and inference. Systems won't be built in a way where every single node looks exactly the same. There will be pools of nodes, some with certain types of accelerators, some with other types of accelerators, all working together to perform different sorts of workloads or to handle different types of tasks. We think that the way that software is delivered in the future for high performance systems is going to change. We've seen an enormous change in the way software is delivered in the enterprise and cloud space thanks to the container revolution. This is something that is just now starting to gain traction in the high performance computing community, and we think that going forward, containers are the way to simplify the ease of deployment for the HPC system administrator and improve the time to solution, time to value for the end user, the research scientist using the high performance cluster. And so we want to bring that philosophy of container first into the HPC space, and that's what we do with Omnia. We do all of this because we want to embrace emerging workloads. It's not just about simulation and modeling. It's not about simply doing fluid dynamics or finite difference or finite element codes. We need to be able to handle distributed and accelerated data analytics. We need to be able to support machine learning training and inference workloads, as well as deep learning training and inference workloads. And all of these workloads have slightly different performance characteristics. They have slightly different developer backgrounds, slightly different tool chains that they rely on. And we need to be able to support all of those in a simple, easy, understandable fashion that accepts the fact that those communities come from different backgrounds and they don't have a traditional simulation and modeling pedigree from which to build. We also want to take advantage of many of the software-defined tools that have come out of the cloud service provider and enterprise space over the last decade. In the last decade, we've seen the growth of data center space that is not based in high-performance computing, and they've built an entire tool chain around different technologies. They're not building clusters of tightly coupled systems. They're building pools of resources that they can reconfigure and redesign at any time. And we want to take those same concepts, those same tools, and apply them to the high performance computing space so that we can rapidly deploy solutions. We can expand those solutions with additional infrastructure, easily tear down short-term solutions, and do everything with repeatable infrastructure as code practices. And so the Omnia project is an open source framework for composing high performance clusters using a lot of these modern DevOps tools, these modern capabilities, and embracing a lot of these more modern philosophies about software delivery and distribution. It's a community-driven effort started by Dell Technologies in partnership with Intel, but we have other community members as well, including the University of Pisa, Arizona State University, and Visius. We also have contributors from various institutions around the world, including Tennessee Tech University, Baylor University, AstraZeneca, Google, and VMware. You can find Omnia online at GitHub. If you go to github.com/dellhpc/omnia. And because we're community driven, because we're open source, we're not trying to reinvent the wheel. We really want to be able to leverage best of breed software products that already exist in the space, whether that's lower level tools such as DNS or key value storage systems or software defined networks for Kubernetes, or workload managers such as Slurm, Kubernetes, and eventually a growing list of other units as well. We want to be able to take advantage of anything that exists out in the community that's going to perform the job that we need it to perform. And that goes all the way up to user software coming from Intel's One Container portal, which features containers built on top of the One API software stack, including One DNN, One MKL, and the Intel MPI stack. Spark, OpenHPC, TensorFlow, and PyTorch. We want to leverage all of these pieces instead of recompiling, rebuilding, and resupporting a whole new stack of software. And this extends all the way up to the user platform space. We support Kubeflow and Polyaxon, and we're working with the team at Converge.io in order to provide Converge.io support on top of Omnia clusters. You can see on the right the two different types of stacks that Omnia currently deploys. The one on the top is a minimal Slurm-based stack that uses Singularity as a container runtime. And the idea is, because we're container first, we don't need to install an enormous amount of user software on top of the system. We actually only install 3 things. We detect whether or not there are accelerators in each individual server. And if we find them, we will go ahead and grab the appropriate driver software stack from the internet, if we can find it in an open repository, and we will install it automatically. We then install the container runtime, which is Singularity in the case of this stack, and then we install Slurm on top of that. And then all the other software is brought by the user. It's brought from the community. So instead of the HPC system administrator having to install all of the software in order to turn it into a functional cluster, that software just comes from all of the great work that's going on at the various technology vendors, such as Intel, who's done an enormously impressive job putting together the one container portal with all of the one API-based software inside of it, or other libraries and registries and portals that exist out there. On the bottom, you see the container native stack. So this is the Kubernetes-based stack that we run for doing artificial intelligence, machine learning, data analytics, and persistent services sorts of workloads. Again, we automatically detect all of those accelerators in the box, and if we can find drivers for them, we will go ahead and install them. We install container runtimes, the orchestrator itself, which is Kubernetes. We install various operators and extensions on top of that, such as the MPI operator, Spark operator, the NFS client provisioner, which help to turn that Kubernetes cluster into something functional, providing you access to capabilities and storage and networking and pod coordination that you wouldn't have otherwise. We also install load balance and ingress tools such as Metal LB, so you can provide IP addresses or DNS names to your persistent services. And then we can install user platforms on top, again, like Kubeflow, Polyaxon, Converge.io, or Jupyter Hub. And all of this is done in a one-touch fashion using Omnia's intelligent cluster deployment system. And the intelligent deployment feature of Omnia is done in a 3-step process. So the first thing that Omnia does is it inspects the contents of every single server in the eventual clustered solution. Instead of assuming that everything has the same configuration, we assume that nothing has the same configuration. We look at every single server, we collect the information about that server, its OS, the contents of the box, what network cards it has, what accelerator cards it has. And once we've inspected that system, we can then install all the appropriate software needed to help turn that individual server into a piece of a fully integrated clustered solution. So accelerator drivers, container runtime systems, workload management software, all of it installed automatically by Omnia. And once the installation step is done, we then integrate all of those pieces together. We configure all of that installed software, and we have all of the servers joined together so that you're left with a fully integrated cluster that's ready to go. Like I said before, Omnia is all open source, but there is a pro support option available from Dell Technologies if you're running Omnia on top of Intel-based PowerEdge platforms. And what intelligent cluster deployment does for us is provides us enormous flexibility and gives us the ability to maximize resource utilization. Now, if we imagine that we were setting up an HPC cluster on this pool of resources, a traditional HPC deployment tool, which couples the deployment and provisioning together, where you put all of the application software inside the image with the operating system, would build one cluster. You'd build a single cluster. All of the units, all of the servers inside of this resource pool would be part of a single cluster. And Omnia can do that too. So you can use all of your resources to build a single large-scale cluster if that's what you need to do. But by decoupling deployment and provisioning, we can actually do much more interesting things on top of a pool of pre-provisioned resources that have a minimal OS. We can start to think about dissecting this resource pool into various parts and creating logical clusters out of these resources, some of which are intended purely for simulation and modeling, some of which are intended purely for ML ops and AI and machine learning exploration, some of which are intended for both, for those situations where you want to build clusters where you're going to have simulation workloads that are calling inference services that might be run in a Kubernetes cluster. You can run all of that together on the same cluster. And you can mix and match all of these capabilities together so that you build the right clusters for the problems you need to solve at the moment. And when you're done with them, you just tear them down. And those resources are available to use for a different cluster if you need to. And all of this intelligent deployment is done by the Omnia control plane. The control plane itself is an Omnia solution, something deployed by Omnia itself. So Omnia can bootstrap its own control plane, and the control plane handles these three major capabilities. It does the bare metal provisioning of that minimal operating system, and it does that by automatically detecting and configuring that infrastructure through the iDRAC out-of-band management controller or using Pixie. Once that resource pool is created and those minimal OSs are provisioned, we can then do all of that intelligent deployment right on top of the resource pool from the Omnia control plane. The control plane also gives us the ability to scale and resize all of those on-demand clusters to better utilize the resource pool. It provides a way of doing zero-touch provisioning of that operating system and then a one-touch deployment of a logical cluster. And Omnia is really redefining how users interact with high-performance software. In a traditional HPC cluster, you would have a software environment that looks very similar to this. You would have multiple compilers, multiple MPI libraries, and multiple math libraries, and you would build the same application for each of those combinations of math, MPI, and compiler. And so in this situation, we have 18 different application binaries, but we're only having 3 applications. You can see that they're just repeated over and over again. And this becomes a very tedious problem for HPC site administrators, for HPC software administrators. They have to be able to manage all of this. And there are tools like modules that help the user manage all the complexity of the software stack. But in the end, it's an enormous amount of effort, and it doesn't have to be that way. And so Omnia reimagines how users interact with the HPC software stack by just leveraging existing compilations, existing builds in containers. And we use the Intel One Container portal as the primary source for those containers. We can pull various containers that include compilers, MPI libraries, math libraries, all of those pieces down together. Those containers are optimized by Intel, and we know that they work. But if for some reason you need a container from somewhere else because it doesn't exist in the Intel One Container portal, you can get them from other places as well, including OpenHPC, Docker Hub, Quay, or even a local registry you set up for yourself. If you have specialized accelerators, it might be worthwhile to pull a container from their registry that's optimized for their hardware. And you can do that as well. Omnia gives you the ability to pull the container you need for the problem you want to solve.
So the problem so thanks, Luke. With the problem we want to solve here is actually deploying all of this hardware in our data center, right? The first thing that we did with the Omnia project was build a control plane. And as Luke said, it was a bootstrap of Omnia. We used the Omnia framework to build a control plane that will control our entire data center. And I wanted to show you how easily you can do this on a single slide with just a handful of commands of really just updating your repositories, grabbing a modern Python and a modern version of Ansible, cloning that repo that we saw out there on GitHub at Dell HPC /Omnia, and running Ansible playbook control plane. And what that'll do, as Lucas said, will go right through your system. It'll grab all the inventories for all of the network interfaces, for all of the hardware that you have in that system. It will boot a Kubernetes-based system on a single server that will then be able to control all of the rest of your hardware in that data center. So Now that you have your hardware all up and running, basically as we rack and stack hardware, that control plane is picking it up, taking in the iDRAC inventory information and provisioning that system, making it ready with a base operating system. Now you can come in here and create a very simple inventory file. We have just 4 very, very basic roles: a manager holding all of the Slurm control D and Kubernetes managed services, an NFS node for storage, a login node for users to interact with your Slurm cluster, compile code, build containers, and things like that, and then compute host to just run those workloads as your users come in. And with a very simple inventory file, we can build a cluster, a logical cluster, out of that pile of metal in my data center by simply editing that little config file, saying which version of Kubernetes do I want? Do I want a login node? And then same thing as we did with the control plane, it's Ansible playbook, omnia.yaml, and pass it your inventory file. And when we do that, we'll just grab those pieces out of the pool of resources that we have to build our logical cluster. We'll use that for some period of time for a research project or for a group of folks who need interactive work, or for folks who are looking to run some long-term persistent services on the Kubernetes side. Now you have your cluster, we have our data center infrastructure, and we want to deploy platforms for our users. We provide a lot of these playbooks right in the GitHub repo for you, a fully configured deployment of Kubeflow. All you have to do is pass it that same cluster inventory file, and you will have a fully functional interface for Kubeflow with pipelines, notebook servers, doing neural architecture searches and Khatib, and all of those sort of fun things. We also have platforms for Jupyter Hub. We're working with the Converged IO folks to have a simple streamline for that. And other interfaces too for our HPC folks, things like the Volcano scheduler and the Spark operator. So really, depending on what workload your users need, you can do a really quick and easy deployment. When I'm actually using the cluster, as Luke said, we don't try to bring in a bunch of software. We tell the users, bring in your own software, bring in the hardware optimized software from your vendor. In this case, we've got a lot of Intel hardware, and so we're using that one API HPC toolkit, and we're just using Singularity. And in this sense, I no longer have to, as a system administrator, provide different compilers, different MPI libraries. We can just pack this all into a container. All of my users can share the same container, and they can build all of their code right off of that. So we can just build code using the Intel MPI C compiler, and we can run it just like we did our regular HPC jobs in a Slurm batch scheduled system. Although instead of using an MPI run or a customized InfiniBand run command, we just use the built-in Slurm S run with the PMI2 interface. And this will tell your MPI applications inside of a Singularity container to how to communicate across your cluster. And you can get that same bare metal performance, but right in a container. Other really useful things that we've seen is the Kubernetes side. So Intel's making it really easy to be able to deploy services such as the TensorFlow serving container. They've made it really simple with simple Helm charts to deploy these sorts of services so that customers can quickly get up and running with ready-made models and start to build their own models and point them into these same serving setups for inferencing on your Kubernetes side. And when I'm done, maybe my project is over, my researchers have moved on to a new project, the funding has ended, I'm done using that cluster, same setup. I just give it that inventory file that we used before, I run the destroy playbook, and all of those nodes are now returned back to the resource pool and now can be reconfigured as another logical cluster when we're ready to do that.
And so this is just the beginning of the Omnia project. We've just released version 1.1. We're rapidly working on adding new features and new capabilities, but we can't do it without the community. Omnia is very dependent on having a strong vocal community to help us know what to integrate in, what to maybe suggest alternative software packages for doing certain techniques and functions. And so it's important that as we grow the Omnia project, we grow the community. And we would love for everyone to become part of the Omnia community. You can find Omnia on GitHub. You just go to github.com/DellHPC/Omnia. Try starring the project, cloning the repo, downloading the release tarball, submitting a bug report, requesting a new feature, or just let us know if you're using it. If you're a member of the Dell Technologies HPC community, you can actually find us on the Omnia channel on the Dell HPC Slack. And if not, you can go to dellhpc.org and join the community and join the Omnia channel there. You can also find us using the Omnia HPC hashtag on both Twitter and LinkedIn. And in addition to just being an individual contributor, if you're an organization or an institution, become a community member. Join us, Dell Technologies, Intel, University of Pisa, Arizona State, and Visias. You can join with us. We will continue to expand the community, expand the amount of feedback that we're getting from the community. We want to make sure that Omnia is the solution that you, as the HPC AI and data analytics community, needs, not just something that we're imposing or that we're providing an opinion on. This needs to be the community's opinion, and we want to make sure that it continues to do that. And with that, I want to say thank you again. Omnia, open source framework for deploying HPC AI and data analytics clusters, started by Dell Technologies in partnership with Intel. It wouldn't be possible without the support of both Dell Technologies and Intel making this possible. You can find it at GitHub or use the Omnia HPC hashtag. Thanks very much.